Hi everyone, my name is Mirela Botezatu. I will present my work on predicting disk replacement. This is a joint work with my colleagues Ioana Giurgiu, Jasmina Bogoiesca and Dorotea Wisman. This is the outline of my talk. First, I will present the motivation, why we think it is important to look into disk replacement prediction. Then we will go and have a look at the data we look for the prediction algorithm. Then I will present our prediction pipeline, the experimental results, and finally we will conclude. Data center downtime costs have increased significantly in the past years, from $5,600 per minute in 2010 to nearly $9,000 per minute in 2016. Batteries, power supplies, disks, they are all culprits of such outages. Disks are among the most frequently failing components in today's IT environments. Now, can we mitigate this issue and can we make these outages maybe a little bit smaller? In the normal scenario, we will have a disk failure, then the failure would be noticed, then this would be followed by a pretty large recovery period, possibly, and then the system comes back to the stable state. What we propose is to have a replacement prediction algorithm in place, which can see when a disk needs to be replaced before time. Then we would be able to schedule the actual disk replacement in time. Then the disk would fail, the recovery period would be very short, and then the system would come back to the stable state much more quickly. Therefore, given the smart monitoring data for the disks, which is the sensors data collected from the disks, we want to provide a subset of smart parameters that are indicative of disk failure. And secondly, using these parameters, we want to build a predictive model that with high accuracy can discriminate between a disk that is healthy and a disk that is likely to fail. The data we use is the smart indicators, as I was saying before. It comes from the monitoring subsystem of the disk, which collects data from different sensors that the disk is equipped with. And we have collected this data from a large population of disks, more than 30,000. Actually, this comes from a data center, and it is collected over 17 months. This data comes along with the labels indicating whether a disk has failed in a particular day or not. An important question is, when is the disk labeled as failed? A disk is labeled as failed when the disk is physically dead, or it does not respond to the commands from the OS, or the RAID subsystem reports that it cannot write or read from the disk. This is a depiction of our prediction pipeline. The prediction pipeline consists of 4 important steps. First, we employ a change point detection algorithm to detect the smart indicators that are indicative of disk failure. Then we provide a compact but highly representative representation of the time series data, which we further feed into the classification algorithm, but not before balancing the data set, which we acquired by an informed downsampling technique. Now I will walk you through each of those 4 steps, and we will start with the change point detection. The goal of this step is to reveal the most informative predictors with respect to the disks at risk. And this is a very valuable information for the domain experts, because right now they use only a handful of these predictors. So our assumption is that when a smart attribute is informative of a disk failure, it would exhibit a significant change in its time series data before the disk is replaced. Otherwise, if the variation is constant or it is uniform, then we would not expect this predictor to have any correlation with the disk failure. So if we have the time series data for a given smart indicator Si, then if there exists a timestamp t when a significant change in the time series of this indicator occurs, then we consider this indicator as a potential attribute that is relevant for the disk prediction algorithm. How we discover these predictors? We approach it in the following way. So first, we use a maximum likelihood approach For a given predictor, we use the maximum likelihood approach to identify the timestamp where the significant change occurs, if any such significant change occurs. Now, having a candidate timestamp, we want to assess whether the change that appears in the time series data is permanent, or it is not permanent and the disk will recover. So if we have gamma as the time series observed after the point t when the change point occurred, and we generate an artificial time series psi that has no change point at time point t. Now we assume that gamma and psi come from distributions p and q respectively, and now we perform a hypothesis test to see whether these distributions are the same, in which case we assume that the change is actually, that the change point did not lead to an unrecoverable error, or these distributions are different, in which case we assess that the change was permanent and it was an unrecoverable error. Now, having reduced the number of features, we want to achieve a compact representations of these features. The observations that lead to the necessity of a compact time series representations are the following. The single-day record is not, it's not good to use just a single-day record as an input to the predictive algorithm, because the disks have recovery mechanisms embedded, and if today we may see a huge number of errors, tomorrow we may see 0 because these errors have been corrected. Also, one should not consider only as labels for the faulty class, as observation for the faulty class. We should not use only the observations from the last day before the disk fails, because otherwise our algorithm will only discriminate between healthy disks and disks that are failing within 1 day. And we don't want this because we want to have timely predictions. So these two observations hint to the necessity of using an aggregate value, and therefore we use a window to split the raw data into segments, and we aggregate each segment via exponential smoothing, and we give exponentially decreasing weight to past observations. Now we have much more observations for the healthy class than for the failed class. The ratio is approximately 50:1. And we know that algorithms are highly optimized for high accuracy, and typically the algorithm would just assign all of this to the healthy class, and then we would have very bad accuracy and precision for the failed class. Therefore, we should downsample the healthy class, and we accomplish this via k-means clustering. So we cluster the healthy observations into k-cluster. K is chosen as a value that is close to the number of faulty disks, such that we have a balanced subset. So we cluster the healthy observations into k clusters, and then we select a number of points that are closest to the centroids of these clusters. And using these points together with the observations from the faulty class, now we have a balanced training set. And now we are ready to feed the data to the classification algorithm. We want to learn a nonlinear function that minimizes a loss, that quantifies the prediction accuracy for the disk replacement problem. And we approach this using regularized greedy forests, which is a variant of gradient-boosted decision trees. And the differences in this algorithm are the following. We induce an explicit regularization term in the objective function. And secondly, it performs a greedy search on the forest structure, changing operations, by always choosing the structure changing operations that minimize the loss. Now, having accurate predictions for a disk model, we want to transfer the learnings from a given disk model to a novel disk model, because we would obtain highly accurate predictions for a specific manufacturer and for a specific disk model of this manufacturer. But can we possibly transfer the learnings to a novel disk model of this manufacturer? And this is what we work on next. And the observation is that disks from the same manufacturer but different model have similar reporting, similar smart reporting, so basically the same parameters are collected, but there is a different distribution of the values reported for the smart attributes. And this is depicted also on the picture on the left. So we use a transfer learning approach. So basically, use the unlabeled data for the new disk model together with the labeled data of the previous disk model to conduct a sample selection debiasing. So if DM1 is the labeled data pertaining to the disk model 1, so for which we have already an accurate prediction pipeline, and DM2 is the unlabeled data pertaining to disk model 2, then we create an augmented data set joining these two samples. And we learn a function f such that f represents the probability of a disk being of model 1 or model 2. Then we sample a subset from disk model 1, the one which has labels, according to this distribution function f. Then we use this subset from disk model 1 to learn the nonlinear prediction function. And now we move to experimental results. In the table, we provide the subset of smart indicators that we used in our prediction pipeline. The two columns correspond to the two disk manufacturers that we have looked at, Seagate and Hitachi. We see that we have much less predictors for Hitachi, and that is because many of actually the predictors were null, and we could not use, therefore, in the prediction pipeline. And also we can see that for some smart indicators, we have a strong correlation for Hitachi, but not for Seagate. One such example is Smart 194 normalized, which actually corresponds to the temperature. And the reason is that actually, if we look at the distribution of temperature in the failed disks, we see that actually Hitachi just had a higher internal temperature, and this explains the higher correlation between temperature and failure for Hitachi. For the prediction accuracy, we have obtained the best performance with the regularized greedy forest, but we have also tried simpler interpretable models such as logistic regression or decision trees. The accuracy we obtain for Seagate is 98% and 81% for Hitachi. This is comparable with gradient boosted decision trees, but regularized greedy forests slightly outperform them. Also, we performed the comparison with the emulated human rules. As I was saying at the beginning, data center administrators typically use only 5 smart indicators to establish whether a disk is likely to fail or not, because otherwise, if they use more, the search space would be very large and not manageable for a human. So we train a decision tree, which basically emulates the type of rules that could be in-house the data center, on a subset of smart indicators that is commonly considered when assessing disk health. And we see that such models have a very small recall of, for instance, for Seagate, only 53% of disks would be detected as likely to fail out of the population of failed disks. Also, we see that the transfer learning approach is showing good results. So we obtain 86% accuracy if we train a predictive model on the subset of observations from the original disk model that are very similar to the observations for the new disk model, compared to the base predictor, which would only obtain 58% accuracy for Seagate. Also, since we have an ensemble of trees, this permits us to extract high confidence rules for this replacement. And we see that, for instance, if smart 197 row is smaller than 2, and smart 188 is greater than 0, and smart 1 normalized is between the given interval, then the disk is healthy with a high confidence. But if smart 197 row is greater than 2, then this disk should be replaced with 100% confidence. Next, we also looked into the early versus the late prediction accuracy. So we looked at snapshots of the disk 1, 3, 10, and 30 days prior to the actual replacement, and we fed these observations to the predictive algorithm. And we see that the predictive power decays the further in the past the snapshots were taken. However, we can have high prediction accuracy even 10 days in advance that the disk actually fails. As a conclusion, we have provided an automatic tool for the disk replacement problem, which we think that has numerous benefits because now the administrators can identify the faulty disks in due time, and also they can back up the data and plan the actual replacement in advance. We have seen that such models are highly sensitive to the number of smart indicators that they use. This explains the 17% difference in accuracy for the two disk manufacturers, for Hitachi and Seagate. And also note that the pipeline can be easily applied to any disk model or manufacturer as long as smart data is collected. Thank you for your attention.
Questions?
Are you able to share what the indicators are? Because, for example, you said the smart 198 is temperature. So are you able to share in English terms what those parameters were in your exercise?
Yes. Actually, you can find the translation on Wikipedia.
Okay.
And I don't have it here, but it's all available in Wikipedia.
Thanks.
Hi, it was a very good presentation. Thank you.
Thank you.
It's here.
Ah, okay.
So, is this code open sourced? My first question.
Yes, we can make it available, the code. We did not upload with the paper, but yes, if you need it, I can share it.
Yes, I would be very interested in that. And then, does the model depends on how many smart variables you have? That the smart.
Yes, yes. Just as I was saying before, that actually the accuracy gap between Hitachi and Seagate is given by the number of smart indicators that we used, because we were able to use much more smart indicators for...
So is it better to have large number of smart indicators?
To have a set that is closer to the set that we have identified to be indicative of disk failure, yes.
All right, okay, thank you.
You're welcome.
Thank you for the presentation. My question is, your accuracy, you mentioned when you calculate that accuracy, what you mean just for the linear accuracy, or you include both linear and non-linear?
Yes, we have computed it separately. First for the replaced class and then for the healthy class.
Okay.
Of course, it's most important to have the numbers for the faulty class.
Yes, yes, because it's in balance. Okay.
Of course, yes.
Thank you.
Yes, welcome.
Anyone else? I have one question. Do you compute the remaining useful life, or just that you're
No, we did not go into survival modeling.
Okay, if there's no other questions, thank God. Speak again.